Hello everybody, Mr. Hendricks here again, and now we're looking at torque and static equilibrium problems. In order for something to be considered in static equilibrium, well first, in general, equilibrium is where there is balanced forces in the system. Okay, so the scenario we're looking at would be this ladder that's sitting on sawhorses here. So there is no rotation going on, so that means there is no angular velocity or there's no angular acceleration. And the whole system, the whole thing is not moving at all, so there's no linear velocity. So in order for something to be considered static equilibrium, the system can't be moving with a velocity in general, and it can't be moving with any angular velocity. So this is a static equilibrium problem that we're looking at solving forces and torque. Okay, so it's a 5.8 kilogram ladder that's 1.8 meters long, resting on two sawhorses. Sawhorse A, which would be this one, is 0.6 meters from the end of the ladder, and sawhorse B, right there, is 0.15 meters from the other end of the ladder. So we can see the radii or the distances drawn here in the diagram. What force does each sawhorse exert on the ladder? Okay, so we're trying to find the force due to this sawhorse and the force due to that sawhorse. So then we have to kind of look at what forces are acting in the system. So this diagram right here shows us kind of a force diagram or a free body diagram, I suppose, of the forces acting on the ladder. All right, and then down below here, that last diagram kind of shows us what we want to pick for an axis of rotation to kind of solve the problem. Okay, so when we're working through these problems here, it's going to be helpful to make an equation with net forces, and then when we actually start to figure out all the torques and stuff going on, we have to pick a point of rotation. So this diagram is going to help us out, kind of tells us to pick this as our axis of rotation, and we'll talk about that here in a minute, but that's what's going to allow us to find all the forces going on here. All right, so let's write our net force equation here. So net force, so that would be all the forces in the system. Right now, nothing is moving, so our net force is 0 newtons. But we can break this down to say, well, what are all the forces that we add together that would give us 0? Well, we're going to have the force of A, and if we're using the diagram over here, A is going up, so let's say up is positive, down is negative. So force of A is going up, and we're going to have force of B going up, so those are going to add together. And then we have force of gravity, that's on that ladder, that's going down, so we will subtract that. Okay. Now we're going to need this equation here again in a little bit. We can make this a little bit nicer. We can just say our positive ones are there as a force of A plus force of B. That's going to be equal to the force of gravity on that ladder, which that makes sense because A and B, the sawhorses, are holding that ladder up. Okay. Let's list our variables. So we have mass of the ladder. Okay. That's 5.8 kilograms. We got G, that's gravity, that's 9.8 meters per second squared. All right, and then really we're going to have to kind of go from here. We got to think about torques in the system. So in order for us to find this, so really the only thing that we have in this equation here is force of gravity on the ladder, which we can find that. So let's do that quick. Okay, so force due to gravity is mass times gravity. So our 5.8 kilograms times 9.8 meters per second squared. Okay, so I'll just write those in there, and that's going to give us newtons. So our ladder will have 57.82 newtons acting on it. So that's the weight or the force of gravity on the ladder. So that would go right there. Right, so we can plug that in if we want to right here. So force of A plus force of B, that's going to be 57.82 newtons. Now, we don't know A and we don't know B. So we got two unknowns. So we got to figure out what to do next. Okay? Well, we know that if we take out one of these sawhorses, that ladder is going to go down, right? That's going to tilt down. And if we took out B, then it would tilt down there. Okay, so there will be some torque involved in this scenario, and that's what we're going to have to use to figure out those forces. Okay, so if we think about the torques that are involved, A, right, if I had A there, that's going to be pushing up, so that's going to cause a torque that way. All right, this one, if I got rid of that, if I got rid of B, that'd be causing a torque that way. Okay, and then B, if I got rid of A, would technically be causing a torque that way. So let's think about all the torques in the system here. So we have torque of A, torque of the ladder, and then we have torque of B there. Okay, so we could kind of, in order for us to figure out our forces here, we can make one of these our axis of rotation, right? So if I have this as the axis of rotation A, as we have listed down below, then our two torques in the system would be that torque and that torque. Okay? So we'd have torque of the ladder would equal the torque of sawhorse B. And then we can go from there. If we think about torques, if I say that A is the axis of rotation, that's not really going to have any torque, right? Because if you had like our two people sitting on a sawhorse, something like that, we just calculated the torque of this person and the torque of this person. We didn't really have to think about the lever or the fulcrum that it was sitting on. Okay, so we're going to declare A as our axis of rotation, and that's going to make it quite a bit easier. So let's say that A is our rotation. The only torques that we have involved here will be the torque of the ladder and the torque of that sawhorse there. So let's say that torque of the ladder is equal to torque of sawhorse B. Okay, so then we can kind of break this up. Well, what's your equation for torque? It's force times radius. So force of the ladder, force of that ladder times radius of the ladder is equal to force of sawhorse B times radius of sawhorse B. Okay, so the radii or the radiuses in here are what kind of lose people a little bit. We know the force of the ladder is 57.82, right? So 57.82, and then our radius of the ladder. So these, the radii here, we have to consider from the axis of rotation. So we said that A is going to be where we're rotating from, okay? So, right, if we took this out, if we took B out of there, then the ladder would just fall down, right? But now B is there holding it up. So we always go from the center of mass when we're talking about these. So from A, where is the center of mass of the ladder? That's going to be right here. So what's my radius? That's that 0.3 meters, okay? And then we have force of B, which we don't know. We can find it. And we need the radius of B. So again, how far from my axis of rotation is that? So we got all the way over here. So how far from A is B? So we got 0.30 plus 0.75. So let's write that up here. So radius of B is going to be 0.30 plus 0.75. Okay. Well, that's going to be 1.05. Okay, because right, 0.3 plus 0.7 would be 1, and then we got 1.05. So now we have enough information here just to find the force of B. So the force of sawhorse B. So let's do that. And we end up getting 16.52 newtons. Okay, so you have to multiply these two and then divide by 1.05, and you'll get 16.52 newtons. Okay, that's the sawhorse B. Now we have this equation that we made before, our force equation. We can use that to figure out the force of A. Okay, that's probably the best way to do it. Come back here. The force of A plus 16.52 newtons equals 57.82 newtons. We just minus, oops, forgot my decimal there, minus 16.52 newtons from both sides, and we get the force of A is 41.3. Okay, so those are the two forces involved acting on that sawhorse. Okay, if we look at all three of the forces, just so we can kind of check our answer, we have the force of gravity, which is 57.82, Force of sawhorse A, 41.3. Force of sawhorse B, 16.52. If you put all those into your equation here, we should end up getting 0. Okay. The only reason we might not get 0 is if we rounded kind of wrong, but it should be close to 0. Okay. So that's how that works for those. So we need to think about our net force, make a force equation. Okay, so this is the force equation that we got to down there. And then we need to kind of pick an axis of rotation in our diagram. So we chose A, and we chose A because that got rid of one of these variables, right? Because if we just chose the center, we knew both pieces of information. We knew force and radius for that ladder, so we wouldn't want to get rid of that because we knew everything. Okay, so that's why we chose A, because we had everything known, one unknown here. Okay, so let's look at another example here. All right, suppose the person lifts the end of the ladder that's nearest to sawhorse B. What force would the person have to exert? What force would the remaining sawhorse exert? Okay, so we got our sawhorse again, or our ladder. This is sawhorse A, and then this is sawhorse B, and then we have a person now lifting that from the end. Okay, so we got gravity there, and those are not perfectly equal. I probably should have drawn them off to the side a little bit. Okay, let's kind of extend this side so it looks a little bit similar to the top. Okay, so we have this person lifting from this end here. All right, so let's list all the forces involved here. So that person is lifting up. All right, so let's draw kind of a diagram on the ladder here. So we have sawhorse A that's pushing up, gravity on the ladder pushing down. Now, is there going to be a force for sawhorse B if this person is lifting it up? No, there will not be, because this person is going to be lifting it off of the sawhorse, so there is no force for sawhorse B, but there is the force of the person there. So force of the person, force of gravity, and force of sawhorse A. So if we think about a net force equation here, again, we're going to say that everything is in equilibrium, so net force is 0. So we're going to have force of sawhorse A plus force of the person, because those are the two that are acting up, minus force of gravity, and that will be equal to 0. Okay, so we have our force equation here, and now we're going to have to pick or figure out torques in the scenario, because we can't just use the variables we had from above, because this person's, like the radius of that of B changed. We have now this guy way out here, so that's going to change our torques involved. Okay, so let's say we're going to pick, let's say we pick A again as our point of rotation. Then if we think about torques involved, we're going to have the torque of the ladder is equal to torque on the person. So the person is lifting up this way, and ladder is going down that way. Okay, so those should be equal and opposite torques. So we have force of the ladder times radius of the ladder is equal to force of the person times the radius of the person. And now we might need to scroll up to look for these again, but we know force of the ladder is 57.82. Okay, and the radius of the ladder was at 0.3 equal to force of the person times radius of the person. So let's scroll up and see if we can pick out what our radius of the person is going to be. So we were going from here all the way out to here now. So we got 0.3 plus 0.75. Well, we did that already. That was 1.05, right? Plus 0.15. So we'd add 0.15 to that because we have all the way out to here. So the radius of that person is going to be 1.2. Okay, so 1.2. So multiply these, divide both sides by 1.2, and we get the force of the person to be 14.46 newtons. Okay, so that is the force that the person has to exert to lift that up. Okay, so that would be the answer there, the force the person would have to exert. So in the second part, what force would the remaining sawhorse have to exert? So that means we're going to have to use our equation here, and we're going to solve for A. So let's plug everything in, see if we can solve for A. So force of A plus that 14.46, that's the force of the person, minus force of gravity, which is 57.82 on the ladder, is equal to 0. Okay, so we'll have to put these together. So force of A minus 43.38 equals 0. Move the 43.38 over. And then we get the force of A is equal to 43.38 newtons. Okay, so again, just like up above, we could plug this in, we could plug this in, and we could plug this in. Those are our three forces. We could plug those into our equation up above, right there, and we should get 0 out of the deal. Okay, so there's a couple of problems involving static equilibrium and torque. So let's look at one more here. So if you wanted to, you could pause the video, see if you can work through this. This one is kind of set up to take you through step by step with A, B, C, D. So see if you can figure it out. All right, so for part A, so let's read the problem here quick. 7.3 kilogram ladder, 1.92 meters long, resting on 2 sawhorses. Again, we got a diagram here. It's kind of nice. We have all the radii or all the chunks there shown. Sawhorse A is on the left, located 0.3 meters from the end. Sawhorse B on the right, 0.45 meters from the other end. Choose the axis of rotation to be the center of mass of the ladder. Okay, so this is where we want to have our axis of rotation right there. Okay, that might change it a little bit. So what are the torques acting on the ladder if this is our axis of rotation? All right, well, we're going to have torque of A and torque of B. Those are the two torques that are going to be acting on the ladder there, because our axis of rotation is that center of mass. Okay, so we could write out a little equation here just to say what our torques are going on. So torque of A is going to be equal to torque of B, and A would be giving a clockwise torque there. B would be giving a counterclockwise torque, but they will be equal and opposite because this is in static equilibrium. And then that would give us, so we break this apart, force of A times the radius of A. So we are 0.66 meters from that axis of rotation, equal to force of B, and the radius for B is 0.51 meters from that axis of rotation. Okay, so this one's going to be going clockwise, that's going to be going counterclockwise. Those are the two torques in the scenario. So for part B, write in it the equation for rotational equilibrium. Okay, and that's pretty much what we did here. Okay, so we could take this one, we could say that this is our equation for rotational equilibrium. Those are the torques in the scenario that will be balanced out. Okay, C, solve an equation for F sub A in terms of F sub G. So before, I'm going to go back up here. So I'm going to write some variables here because I'm going to scroll down so we can have more room below there. So we have a mass of 7.3 kilograms. And let's move this down a little bit. That way we can scroll down and kind of look at our torque still. So everything else is in the diagram. So let's scroll down so we have some room. So C, solve the equation for F sub A in terms of F sub G. So what that is asking, that's asking for a net force equation. Okay, so our net force is 0. And we have 3 forces acting. We have that force pushing up, that force pushing down, that force pushing. All right, so our net force is here. We have so the forces we have acting in this scenario is force of sawhorse A, and we're going to add force of sawhorse B because those are both in the same direction. They're positive because they're going up. And then we have minus that force due to gravity on the ladder. That is set equal to 0. Okay, so we can solve for F sub A. Okay, and that'll help us figure out our force of A. So let's say F sub A. So we would move this over and move that over. So it would be F sub G minus F sub B, right? Because we'd add F sub G to both sides. And then we minus F sub B to both sides. And we get that. Okay, so do we know force of gravity? Yes, because we have a mass of the ladder. So F sub G is equal to 7.3 times 9.8, which gives us 71.54 newtons. So that's F sub G, which we could plug in there in a little bit if we want to. All right, so I think for this one, we want to finish this and solve it. So let's find F sub A. We're going to find force of A in this scenario. So we're going to have to do like we did before. So we're going to have to use these two equations. So this one here, this is our rotational equilibrium equation, our torque equation. And then we're going to have to use this one here to solve. So let's put our force in there. So F sub A is equal to 71.54 minus force of B. So what's nice about this is we have it solved in terms, or for F sub A, and we could take that and plug it into our equation up here. So let's do that. So F sub A is 71.54 minus F sub B. Okay, I plug that in for there, right there, times 0.66 meters. Oops, let's just get rid of that meter there since I kind of, we're going to be getting newtons here in the end because we're looking for a force. Okay, so F sub B times 0.51 meters. And I probably could have written those the other way around. It'd look a little bit nicer. So 0.51 F sub B, kind of like that. Okay, let's move that down. Right there. Okay, so now we're going to have to solve this. So this is some pretty basic algebra here. That's distribute to there, distributes to there, and we get 47.22 minus 0.66 F sub B equal 0.51 F sub B. So now we want to get the variables on the same side, so move this over. Okay, we get 47.22 equals 1.17 F sub B. And then we'll have to divide both sides by 1.17, okay, to get rid of that number in front of F sub B. So divide 1.17, and we get force of B is equal to 40.36. All right, so now we were looking for A, so now we're going to have to take that and plug it in. So F sub A, so force of A is equal to 71.54 minus 40.36. So force of A is 31.18 newtons. Okay, so we have force of sawhorse B, force of sawhorse A, force of gravity. If we added those three together, as in our equation up here above, we would show that they all add together and give us a net force of 0 because this is an equilibrium. Okay, so the last question here, how would the forces exerted by the two sawhorses change if A were moved very close to but not directly under the center of mass? So let's say we take A and we put it here. and we take it out of there. So what happens if we move Sawhorse A there? Okay, well, since this is really close to the center of mass, Sawhorse A would be taking most of the force. Now, we don't know where it's exactly moved to, so we're just kind of predicting here. Like, we can't get any numbers for this question, but A would be taking most of the force, and B would have quite a bit less force on it, right? So B had more force here right now because A is actually further away, so A would have less force, right? So these would kind of flip-flop. A would have quite a bit more force than B, since A would be closer to the center of mass. Okay, so these are some problems involving static equilibrium. Hopefully they make sense. Good luck, and let me know if you have any questions.